So today what I would like to do is go over the atomic radius and the trend that we see on the periodic table. Before we go over that, I would like to go over what atomic radius is. This is going to be defined as 1/2 the distance of a bond. And this is because most elements on our periodic table, when we find them in nature, are going to be in compounds. So they're going to be bonded to something else. So we first measure the length of that bond that we find in that compound. And then we take 1/2 of that, and that's going to be the radius of an atom within that bond. So here, in this picture here, we have bromine. Bromine in nature is found as Br2. So we take the distance of that bond, which is twice the radius of bromine. We divide that in half, and that's going to give us our atomic radius. So what we see on the periodic table is that the atomic radius is the size of a neutral atom, and it increases as we go down the group. The reason for this is if we look at our periodic table and remember our electron configurations, as we go down a group, which is a column on our periodic table, each element going down that column has one more energy level than the previous element. So that means the atom is getting larger as we go down because of a larger number of energy levels. So we add new energy level each time. As we can see in this picture here, the first sphere is maybe with 1 energy level, the second one is with 2, then we have 3, and then we have 4. So we have more energy levels each time. So the radius is getting larger going down a group on our periodic table. However, the radius going across a period, going from left to right, is a little bit more unclear to students, the reason behind that. And we're going to be spending more time on that. So as we go across from left to right, the radius is decreasing. And this is because of something called Coulombic attraction, the attraction between the positive and negative charges. And this is also is increasing as we go from left to right, and we'll go over why. So when we think about charges, there's two things that affect the attraction of charges. One is the size of the charge. If you have more charge present, for example, +2, -2, the attraction between it's going to be greater than less charge. If we only have a +1 and -1, that's not going to be as strongly attracted as a larger charge. Think about if you have very powerful magnets, they're going to be attracted to each other more than weak magnets. The other thing that affects the traction between positive and negative charges is the distance between them. Think about if the distance is very small, as in the top picture, they're going to be attracted very strongly. If the distance is very weak, as in the bottom picture, they're going to be attracted very weakly. So here, what I want to do is I want you guys to imagine that we have a positive and negative charge, and these are attracted to each other somewhat. This is hydrogen, so 1 proton, 1 electron. Now, if we double that charge, so now we have 2 protons and 2 electrons. Now we're imagining helium. Helium, the electrons in the shell, in the first energy level, and the protons in the nucleus are going to be attracted to each other more strongly than with hydrogen because we have double the charge. We have a greater amount of charge. We still only have 1 energy level, so the distance has not changed, but the amount of charge has increased. So as we go across, we have more Coulombic attraction, but no new energy levels. Remember, hydrogen and helium both have 1 energy level, but helium has double the protons, double the electrons. So we have smaller size going across, no new energy levels, but more attraction because more protons, more electrons. So as we go across from left to right, we see the size of the atoms decreases because of the greater number of protons going across. Okay, so let's practice just ranking elements based on their atomic radius from smallest to largest. So I want you guys to try these problems here in number 16 on the sheet I pulled up and try to rank those elements from the smallest to largest. So try that first, and we'll pause this, and then we'll go over the answers. Okay, so hopefully you guys tried that out. So let's go over the answers. So if we look at lithium, carbon, and fluorine, what I want you to notice is all three of those elements are in the same period of our periodic table, so they're all on period 2. And just remember when you're doing this that the radius increases going down, increases going from right to left. And if we look at it, lithium is the furthest to the left, fluorine is the furthest to the right. So fluorine should be the smallest, and then carbon, and then lithium. So if you had ranked that way, you are correct. We look at the next one, lithium, sodium, and potassium. These are all in the same group on our periodic table. Lithium is closest to the top, potassium is closest to the bottom. So they would be ranked exactly as they're written. Now, when we get to something like germanium, phosphorus, and oxygen, these are neither on the same period nor are they in the same group. So in a situation like this, the further down on the periodic table they are is going to be more important than how far over they are in a particular period. So if we look at germanium is in the 4th period. So I'm going to write above this. Actually, I'm going to write down below. This is in the 4th period. Phosphorus is in the 3rd period. Oxygen is in the 2nd period. So this means automatically, without looking at where they are as far as how far over they are on the left or on the right, that germanium would be the largest, that phosphorus would be the 2nd largest, and then oxygen would be the smallest. If we look at carbon, nitrogen, and aluminum, we notice right away that carbon and nitrogen are in the 2nd period, so they're both in the 2nd period. Aluminum's in the 3rd. Now, when you're comparing elements in the same period, if you're not as visual, another thing you could think about is how many protons are in the nucleus. So if we think about carbon has 6 protons in the nucleus, nitrogen has 7. They have the same number of energy levels. Both carbon and nitrogen only have 2 energy levels. However, nitrogen, with its greater number of protons, is going to be pulling those 2 energy levels in more. So of these two, nitrogen is going to be smaller than carbon. So aluminum will be the largest since it has 3 energy levels. Carbon will be the 2nd largest because it has 2 but fewer protons to pull those electrons in. And then nitrogen will be the smallest because it has 2 energy levels and 7 protons pulling those electrons in. If we get down to the last example here, we have aluminum, which has 3 energy levels, chlorine, which also has 3, gallium, which has 4. So again, gallium, we know right away, is going to be the largest with its 4 energy levels, so I'm going to rank that as the largest. And now we're comparing aluminum and chlorine. Again, if you're not as visual, look at the number of protons. Aluminum has 13, chlorine has 17. They have the same number of energy levels. Aluminum, however, is going to be larger because there's fewer protons pulling those 2 energy levels in. So that would be aluminum. And chlorine will be the smallest since it has those 17 protons pulling in those 3 energy levels in.